Hello everyone, I am Aadarsh Pathak. I am currently a PhD student at University of Melbourne. The project which I am showing here is basically my master's project which I am showing. So here we have mostly focused on the largest ionized region in order to see that whether we can distinguish between the different ionization models or not if we are following just the largest ionized one. So this is the cosmic evolution figure, cosmic evolution history of our universe. My research interest is basically the epoch of reionization. And we wrote that if we want to probe the epoch of reionization, we mainly have to consider the two things. First is we have to simulate the IgM, and second, we have to see the effect of different sources. Now, simulating the IgM means we have to consider the dark matter and the baryonic stuff. If we are talking about baryonic stuff, then I'm using the neutral hydrogen because of the fact that this is the most abundant element we have in the baryons. So we are particularly using the 21 centimeter wavelength emitted from this neutral hydrogen for that. Now, the second important thing is the effect of different sources. So in practical, there could be a large possible sources which basically ionize the IgM. Here I'm considering 4 such source models. So in these models, we have assumed that the number of ionizing photons emitted by these sources is basically proportional to the halo mass in which they are basically residing. So the first one and the first and the last one is basically the same. Both of them are emitting ionizing ultraviolet photons. But the power law model is basically emitting the ionizing photons from the halo masses, which are having the power of index 3. And the first one has the index of 1. The middle two are known to emit hard X-ray photons and soft X-ray photons, depending upon their mean free path. Now, to increase a little bit complications, we have used these 4 source models in different ratios of proportions to define our 6 reionization scenarios here. So the first two are emitting ultraviolet photons, where the clumping model is using the non-uniform recombination. The PLN is equal to 3 has already been discussed. The next two are basically showing the dominance of hard X-ray photons and soft X-ray photons with 80%. And the last one is a mixture of hard X-ray, soft X-ray, and UIB photons. This is the 21 centimeter brightness temperature map for these 6 scenarios. We can see clearly that the pace with the pace at which the ionized regions are basically being evolved is different for different models. So for model like power law, we will have the ionizing photons is basically propagating or evolving at a very faster rate as compared to the UIB photons. So we were interested to see that if we will follow the largest ionized region, whether we will be able to distinguish between these reionization scenarios or not. So for that, we have used the Subgen2 algorithm. So it is a surface generating algorithm which identifies the shapes and sizes of our ionized regions. So we give the threshold on the basis of which it basically triangulates the surface and it calculates the Minkowski functionals. So there are 4 Minkowski functionals which gives the geometrical and topological information of our object. So if we have an object, then it will give us information about the surface area, volume, concavity or convexivity the surface can have, and somehow the topology if they have the genus or holes in between. Now, once we have these 4 Minkowski functionals, we can use them in 3 different ratios to define our 3 shape finders as thickness, width, and length. Now, these 3 shape finders can again be taken in different ratios to define our 2-dimensionless quantities, which are planarity and filamentarity. Now we can compare these planarity and filamentarity to info about our shape. So if we have a P much greater than F, then we will have planar structure, otherwise filamentarity and so on. So this is all we have in this fund. So in a nutshell, what we are doing is that we have used the simulated H1 21 centimeter map of these 6 reionization scenarios. And we have basically applied this on the Subgen2 algorithm, and on the basis of which we are seeing the evolution of our largest ionized region. So based on the things, let us discuss the results now. Here on the left-hand side, I have shown the neutral fractions variation with respect to the neutral redshift. So in our all reionization models, we have kept our neutral reionization history same. So at any particular redshift, our all reionization scenario will always have the same neutral fraction. But if you look at the right-hand plot here, we can see here we have plotted the filling factor with respect to the neutral fraction. And filling factor is defined in this way that if we have a simulation box, then the ratio of the volume of all ionized region in my simulation box with the ratio of the simulation box. So we can see here that the filling factor is increasing, and for different ionization scenario, we have the different filling factor. This shows the properties of our ionizing sources. That although we have the same reionization history, our and the way the way the neutral ionium is being ionized is different by different ionization scenarios. Even if you look at the number of ionized regions formed by these scenarios, we can see that few of the scenario like UIV dominated forms the largest number of ionized regions, while the scenario like power law forms the least number of ionized regions. But their contribution in the filling factor is significantly different, which again signifies the property of our sources. Now here I plotted the largest cluster statistics with respect to the neutral fraction and filling factor. Largest cluster statistics is basically the ratio of the volume of my largest ionized region with respect to the volume of all ionized regions in my simulation box. Here the vertical dashed line shows the point of percolation. So it's the instance when the different isolated ionized regions will basically connect with each other to form a single large interconnected one. So we can see clearly that as the reionization progresses, the LCS evolves, and the evolution is the trend of evolution is almost similar, but the different ionization scenarios are basically percolating at different neutral fractions. So if we are following the evolution of LCS along with the percolation, we can somehow distinguish between the scenarios, and especially we can categorize them into two broad categories of reionization, which are inside out and outside in. So in inside out, the high dense regions are ionized first, then the lower dense regions will be ionized, and opposite is happening in the outside in. Here, the right-hand plot just shows the fact that at the end of the reionization, we will have the maximum contribution from our largest ionized region in our filling factor. Apart from this LCS, if you are following the largest ionized region, we can infer something about the shape of our ionized regions as well. So here I have plotted the cross section and length of our ionized region with respect to the neutral fraction. Here the vertical dashed line shows the point of percolation. So on this side, we will have the point before percolation. On that side, we will have the point after percolation. So we can see that as the reionization progresses, the cross section almost remains same, but the length increases several order of magnitudes, which confirms the fact that at later stage of mainly after percolation, we will see the filamentary structure from almost all the reionization scenarios. Although there is a discrepancy in the clumping model because this is the only model where non-uniform combination was considered. We can also sense something about the multi-connectedness we observe at the later stage. So if you follow this figure here we have plotted the genus with respect to the neutral fraction. So genus, as I discussed, that it represents the number of holes we have in a simple way. So as the reionization progresses, the genus value increases, which confirms the fact that with the progression of reionization, these filamentary structures will basically connect with each other, and it will create multi-connected ionized regions later on. So this is all, and with this I can conclude my discussion here. So we have tried to use the largest cluster statistics in order to distinguish between the different reionization scenarios. And we can somehow distinguish between the scenarios, and mainly we can categorize them into two broad categories of reionization, which are inside out and outside in. And although different ionization scenarios are showing different kind of properties in terms of ionization, but later on, all of them are going to show the filamentary topology after percolation. Thank you.